Good afternoon to all of you. In this lecture, we have to start with frequency modulation, behavior of frequency modulation in presence of noise. In last lecture, we have studied with angle modulation and we specifically with phase modulation. In that case, we can say that signal to noise ratio, output signal to noise ratio is directly proportional to square value of transmission bandwidth. That means when we increase the bandwidth, signal to noise ratio is increases. When we doubling the bandwidth, signal to noise ratio increases with 6 dB. This is true only for small noise case, that is En of t is very much small than the amplitude capital A. So for the case narrow band noise where bandwidth is given as 2 into delta f plus b, it is true for small noise case. For wide band FM where bandwidth is infinite, this is not true. Now in this case for FM is nothing but extension to phase modulation. Here we are using integrator. Input to integrator is m of t. Then we are having phase modulator. Here input is Si of t. Here Si of t is frequency modulated signal. Noise is going to add Ni of t, which is given to phase band pass filter, and finally we have to use differentiator, which will give the output S0, that is equal to Kf into m of t. This is a general block diagram for frequency modulation in presence of noise. It is an extension to your phase modulation. M of t is the signal, message signal with bandwidth capital B. Here we have to use the integrator, then phase modulator, input to phase modulator, input to demodulator is nothing but your signal Si of t, which is a frequency modulated signal, noise Ni of t, which is a AWGN noise, adaptive white Gaussian noise, which can be represented by its quadrature representation in phase component and quadrature component, which is a input to this demodulator. Phase PM band pass filter, then demodulator, followed by this differentiator, and finally we will get this S0 is equal to Kf into m of t. So here we will get S0, that is equal to Kf square m square bar into a cos of omega ct plus Kf integration of m alpha into d alpha. Only change due to this integrator, we will get Kf into integration or m alpha into d alpha. Here we will get noise, that is S0, that is equal to n by a square. N is the peak amplitude for white Gaussian noise and a is the amplitude. Here we are interested to find out the output signal to output SNR in terms of input SNR, in terms of its bandwidth and all these cases. Here output SNR is given as n by a square into omega square, where omega is ranging less than or equal to 2 pi b and 0 otherwise. The transfer function for this differentiator is given as j omega. So whatever the output at output of your demodulator is get multiplied with this transfer function j omega. Here s naught is get, we are having the derivative of this quantity. Similarly, the noise which is present at this point is get filtered out or differentiated by using this quantity j omega. So here this s naught of omega we will get, or this minus b to b two pi b to 2 pi b this is the power spectral density or the noise which is filtered out from this phase modulation system. So here we will get average power over this noise 0 to b n by a into 2 pi f square into df. So here we will get 8 pi square n into b cube divided by 3 square. Is it clear to all of you? Here input to differentiator is nothing but input from your phase demodulator band pass filter. Here at output we will get s naught, that is equal to kf into m of t, kf into m of t, and noise, whatever the noise, it will give this spectrum PSD, power spectral density, for your noise which is get filtered out from this derivative function. So here average power over this noise is given as 2 into integration or 0 to b n by a square 2 pi f square into df. Here 2 pi f is nothing but j omega. This is the transfer function for this one. So it is equal to 8 pi square n b into cube divided by 3a square. Now we have to calculate output signal to noise ratio, that is s naught divided by n naught. Here this is given as 3 into kf square m square bar. Output is s naught, that is equal to kf into m of t, or this one we have to find out the average power kf square into expected value of m of t square divided by 2 pi b square into a square by 2 divided by nb. That is equal to 3 into kf square m square bar divided by 2 pi b into gamma. Gamma is nothing but input signal to noise ratio. So here we are having delta omega is equal to kf into mp, kf into mp. This is the frequency deviation. So signal to noise ratio is given as 3 into delta f divided by b square So this is equal to 3 beta square into gamma m square bar This is the output signal to noise ratio for FM, where we have to consider noise is AWGN. This is given as 3 into beta square into gamma m square bar divided by mp square. Here beta is modulation index, gamma input signal to noise ratio, m this is the average power or your message signal, and mp square this is the peak value. So for tone modulation, write down, for tone modulation, where m of t is a sinusoidal signal, this ratio, that is m square bar divided by mp square is equal to 0.5. For tone modulation, this ratio m square bar divided by mp square is equal to 0.5. This is the case for tone modulation, where m of t is a sinusoidal signal. For this case, we will get signal to noise ratio for FM, that is equal to 3/2 beta square into gamma, and signal to noise ratio for PM is 1/2 into beta square into gamma. Just compare these two quantities, output signal to noise ratio for PM and output signal to noise ratio for FM. Write down, FM is better, FM is superior by PM by the factor of 3. By the factor of 3. Are you get it? Output signal to noise ratio for FM and PM. For FM, that is equal to 3/2 beta square into gamma. Here beta is your modulation index, gamma is nothing but input signal to noise ratio. 3/2. Here 3 quantity is present. For PM, it is 1/2 beta square into gamma. So for same input signal to noise ratio, for same beta, for same bandwidth, we will get FM gives the superior performance by the factor of 3. Means we will get a highest output signal to noise ratio. When we compare this angle modulation with AM modulation, which one is the better? Angle modulation is the better. What is the limitation for your amplitude modulation system? Bandwidth. Bandwidth is the problem for your amplitude modulation system. This will be overcome in your angle modulation system, but working in the area of small noise case. Then what is the problem? What is the problem for angle modulation system? Yes, this is one point. That angle modulator system gives the better performance than your amplitude modulator system, because it is having the bandwidth is higher. For wideband FM, bandwidth is infinite. For narrowband FM, bandwidth is 2 into delta F plus B. We will get a better bandwidth. Yes, we are working in small noise case. En of t is very much smaller than amplitude A. Then what is the problem? In which sense? We are not talking in hardware point of view. We are talking in the sense of noise. It is going to add in your modulated signal. It is having the white nature, that means we are having a uniform power spectral density with the height capital N by 2 for all the frequencies. It follows the Gaussian nature, that means it follows the central limit theorem. Gaussian nature, that means it will give the normal distribution. Then what is the limitation for this angle modulated system? Here gamma threshold is approximately equal to 20 into beta plus 2. Gamma threshold for angle modulated system, that is equal to 20 into beta plus 2. That means this threshold value depends on beta. Beta is related with your bandwidth. As we increase the bandwidth, this threshold point is also increases. That means it is shifted. So when we plot the output signal to noise ratio in terms of input signal to noise ratio for your communication system, when we are talking about your AM modulation, for your AM modulation, when we consider synchronous detector, we will get a linear relationship. Output signal to noise ratio is related with your input signal to noise ratio with some slope. Depending on this slope value, we will get output signal to noise ratio. For envelope detector gives a linear relationship it will give the linear relationship above the threshold point. This threshold point, that is gamma threshold, it is the point, that is the input signal to noise ratio, minimum input signal to noise ratio, below which your system get distorted. We are not able to hear the songs. When we are working below this region, here input signal to noise ratio is minimum. Here output signal to noise ratio is minimum for this region. So for this region we have to avoid this region for proper working of amplitude modulation. When we are working with your envelope detector, when we are working with your synchronous detector, there is no problem. We will get a linear relationship. Now here generally for AM we are working with your songs or voice communication. This gamma threshold is minimum. There is no effect of gamma threshold in AM modulation. But when we are moving towards your angle modulated system, for angle modulated system, when suppose this beta is increases for beta 1, this is your gamma threshold for beta 1, again you have to increase bandwidth, that is your beta 2, this is the gamma threshold for beta 2, this hike is 6 dB, gamma threshold beta 3. I got the limitation of angle modulated system. Benefit is, as we are increasing the bandwidth, output signal to noise ratio increases. When we compare this angle modulated system, we will get a better performance than your AM modulated system. Here it is get shifted, it is get shifted, it is get shifted. Then problem is lying here. As we are increasing the bandwidth, this gamma threshold point is shifted. Just assume that for AM, this is supposed to 10 dB. So we are working about 10 dB. For your angular modulated system, when we are increasing the bandwidth, suppose this is your 20 dB. As we are increasing this value, 30 dB, 50 dB. Now in present situation, I have input signal to noise ratio is ranging between 25 dB. So I have to select either AM, I have to select for AM which gives the gamma threshold value, that is 10 dB. So my working area is above the threshold value. Here for this 20 dB, yes, I can increase the bandwidth, I can move towards angle modulated system where up to the bandwidth for this gamma threshold beta 1. When I have switched for B2 higher bandwidth, then what happen? What happen? This gamma threshold value, that is for this second bandwidth beta 2 is higher than my signal level, 25 dB. This is 30 dB. So definitely you will get a distortion in your angle modulated system. When you are listening songs on your FM, when this bandwidth is lower than gamma threshold value, definitely you will get a noise in your system. I got the concept? Just write down this point. Angle modulated system gives a better performance than amplitude modulation system, above the working above the threshold values. I got it? In angle modulation, we are having frequency modulation system and phase modulation system. We are having FM 91.1 FM. Here in angle modulation, we are having FM and PM. From this formulas we can say that output signal to noise ratio for FM is superior than PM by the factor of 3. This is one reason. For your angle modulation system working in large noise, that is the case where AN of t is very much larger than capital A. For small noise case, delta psi of t, this is the quantity which will give the measure of noise effect. For small noise case, this is a less than delta psi of t is less than 2 pi. We can say that for small noise case, variations on delta psi of t are limited. For this case, when En of t is very much larger, the magnitude of amplitude of noise envelope is larger than amplitude of message envelope. In this situation, variations on delta psi of t, they are in terms of 2 pi. They are in terms of 2 pi. For your phase modulation, where we are having delta psi of t, see here, these are the variations here. Suddenly we will get variations of 2 pi. Here variations of 2 pi. There are large variations. For your FM, for your FM, in FM we have to take a derivative of phase, derivative of this delta psi of t. See here, for angle modulation, all the information is hidden in psi of t, which is proportional to your m of t. This is the case for your phase modulation. For frequency modulation, instantaneous frequency deviation, that is derivative of psi of t, is proportional to m of t. This is the case for FM. All of you agree? Yes or no? In angle modulation system, delta psi of t is the quantity which will give the effect of your noise. For small noise case, variations of delta psi of t, they are less than 2 pi. For large noise case, where En of t is very much larger than A, we will get a larger variations. 2 pi, this is your 4 pi, then your 6 pi. These are the variations in your phase. But when we are looking towards your FM, in your FM we will get a derivative of this psi of t. So for a very small duration we will get a hike, we will get an impulse in your FM. For this very small duration we will get an impulse. Here we will get an impulse. So in your FM suddenly we are having a noise. So noise is present, which is a present for very small duration. I got it? This is a present for very small duration. Yes, we can sustain with small noise. We can sustain with this small noise. As compared to this one, in phase modulation, this quantity is increases. This quantity is increases. So we can say that in your FM we are having click noise or crackling noise. Write down click noise, click noise or crackling noise. So FM is better than PM. First reason, FM gives the superior performance by PM by the factor of 3, because its output signal to noise ratio is that is equal to 3 divided by 2 beta square into gamma. This is first reason. Second reason, in PM for large noise case, in noisy environment, heavy noise environment, your PM get failed out, because we will get a larger variation in delta psi of t. These variations are in terms of 2 pi. First rotation 2 pi, second rotation 4 pi, third rotation 6 pi. But in the case of FM, we are having the derivative of delta psi of t as a demodulator. At output we are having a differentiator. This will give the derivative. Here at suddenly for very small duration we will get an impulse of some height. This is called as crackling noise. But for other duration, performance of your FM is quite good. In pulse modulation, first point we have to see this sampling theorem. So in this pulse transmission, we have a signal which is an analog signal G of t. Analog signal G of t is get sampled. Here we are using a impulse function, one delta t or ts, where duration between these two impulses is given as ts. That means sampling frequency is fs with unit amplitude 1, and here we are having the frequency response. This signal G of t is band limited to capital B. It is band limited to capital B. Its bandwidth is capital B. Center around your zero frequency. It is band limited with amplitude A. It is get multiplied. The signal is get multiplied. So we are constructed this G of t. G of t is a sample value, sample signal. So this G of t, its Fourier representation, frequency representation, we will get at zero frequency omega s, 2 omega s, and so on. That means these are the various samples for various impulses. As your this signal, impulse signal is nothing but periodic signal. It is a periodic, get repeated for Ts time, for the fundamental period Ts. This is get repeated. It is a periodic signal. So we can represent this signal by using your Fourier representation. So write down here g of t is band limited to capital B hertz g of t is band limited to capital B hertz. Delta of t or capital Ts, delta of t or capital Ts is a unit impulse train. It is a unit impulse train consisting of unit impulses repeating periodically every Ts, capital Ts seconds. So capital Ts is equal to 1 by Fs, sampling frequency, resulting g of t bar this represent sample values, that is nothing but g of t analog signal multiplied with impulse signal. This is in continuous domain. For discrete domain we can see that summation or n g of n into Ts delta t minus n of Ts. Single impulse function is get shifted. Initially suppose this is presented here, it is get multiplied. Suppose this is your n is equal to 1 sample, we can get a sample value for this n is equal to 1. Suppose this is the value corresponding to n is equal to 1, so we will get g of nt, here n is equal to 1, that is equal to g of nts, that is the sample from this value. This sample value, amplitude of analog signal, that is g of t, at this point is get multiplied with n is equal to 2, n is equal to 1, this impulse value, they are get multiplied here, n of ts, amplitude of g of t at this point, impulse train, that is a unit impulse, is get shifted, that is t minus ns of t, it is get shifted. Suppose this is initial position, it is get shifted towards left. Continuously your impulse function is going to shift on this g of t. So finally we will get this structure. Finally we will get this structure where we are having the multiple values which are discrete for this g of t. Is it clear? Here we can see that this impulse function is a periodic, so we can represent this impulse function by using Fourier series. So write down representation of delta t by using Fourier series, that is equal to C0 plus summation or n Cn into cos of n omega st plus theta n, where omega s is equal to 2 pi ts, omega s is equal to 2 pi ts, or sorry, omega s is equal to 2 pi fs or 2 pi divided by ts. So we have to calculate this component a0, an and bn. So this, it can be represented as 1 by t as 1 plus 2 summation n is equal to 1 to infinity cos of n omega s t. So 1 by t s 1 plus 2 into cos of omega s t plus 2 into cos of g of t So we will get g of t bar, that is equal to 1 by ts, g of t plus 2 into g of t cos omega s t plus 2 into g of t cos 2 omega s t, that means multiple values. So we can represent in frequency domain, that is capital G of omega bar is equal to 1 by ts summation or n is equal to minus infinity to infinity g of omega minus n omega s. So here we can see that to construct g of t, write down, to construct g of t from g of t bar, to construct g of t from g of t bar, we should able to recover capital G of omega, capital G of omega from capital G of omega bar. It is possible if there is no overlap between successive cycles, if there is no overlap between successive cycles of G of omega bar, For this we requires sampling frequency fs. It should be greater than 2b, 2 into capital B, 2 into capital B, and capital Ts it should be less than 1 by 2b. Minimum sampling rate fs is equal to 2b. Minimum sampling rate fs is equal to 2b required to recover g of t, from its samples. G of t bar is called Nyquist rate for g of t. Now in this context we can see that our job is we have to see the behavior of digital modulation system in presence of noise. So first of all, you have to identify which type of noise is going to occur in your digital communication system. In analog communication system, noise is generated by your transmitter, receiver and channel. Collectively we can say that this is your additive white Gaussian noise. Here we can say that this noise is, we are having the two possibilities at receiver side to getting an error for reconstruction of signal. First thing is your aliasing effect and second one is your quantization error. In next lecture we have to see this.